Welcome back, Honors Algebra 2 kids. Mrs. Fallon here. I am on page 228 of your student journals. We're going to talk through section 8.3, which is about geometric sequences and series. So in the last video, I talked a lot about arithmetic sequences and series and what that kind of represented, right? And that was that relationship, that linear relationship that we are somewhat familiar with. I know that many of you have, especially in Algebra 1, you might have explored with the function exponential functions. And so as a quick reminder, an exponential function, for those of you who know what I'm talking about, is one of the functions in, again, if you were looking at the graph, it would look like a big kind of like, it would start off slow and then go really quickly. It would increase really rapidly, or it would start off decreasing really rapidly and then leveling out. So if you're looking at the table of an exponential relationship, what you would notice is that the difference between the values. So like, you know how in a linear or an arithmetic sequence, the difference between the values is a constant, right? We call that the common difference, we call that the slope. Well, in exponential relationship, what you learn is that you're multiplying by a constant amount. And we talked about the common differences and all that kind of stuff. Well, that's what we were referring to when we talk about a geometric sequences and series. It's representing an exponential relationship. So if you know what I'm talking about in terms of, if you know what an exponential relationship is, this will be review. If you don't know what an exponential relationship is, then this will be something that's kind of brand new, but that's okay, because we're going to kind of talk about it in a little bit general terms, and we're actually going to get into exponential functions in a lot more detail later on in a different unit. All right, so what an exponential relationship is, and the thing I want you to kind of remember, is it's the ratio of any term to the previous term is constant. So they call this the common ratio, okay? The ratio from any term to the previous term is constant. Sometimes I think it's helpful if I give you kind of a for instance. So what I mean by that is, let's say I give you 2, and then I tell you this is 6, and then I tell you the next term in the sequence is 18, and then it goes on forever from there. What we notice here, unlike a common difference where like you're adding and subtracting by a constant amount, what you should be noticing here is that you're multiplying by a constant amount. And so that value that you're multiplying by is what we call the common ratio. And so R is what we represent the common ratio as. All right. So again, it's a little bit different, obviously, same kind of general idea, just a different pattern that we're noticing. And just like with arithmetic, geometric series is when you add the terms. So you're going to add the terms of the geometric sequence. And so we are going to learn a couple formulas. So if you have that formula page that we've kind of been working on earlier, let me see if I can find mine. Go ahead and grab it, because we're going to need it here in a second. All right. So the first thing I want to look at is the kind of the equation for like the general equation. This is what we've done with the arithmetic. We did this with arithmetic. So this is our kind of our general equation to represent all all relationships or all geometric relationships. And so this is the formula we're going to kind of memorize. It's a sub n equals a sub 1 times r to the n minus 1. And so what I want you to get out of that is then just kind of like, what do these things represent? Let me find my paper here that has all my, there we go. Okay. So our formula page that we kind of talked about in the last video. So now what we're going to do is we're going to add on a whole section of geometric. There's actually a few more equations with geometric than there are with arithmetic. So the first one is that common, that basic a sub n term. So again, what I want you to represent here is that a sub n represents any term in the sequence. So if we were talking about the 52nd term, whatever the 52nd term would be what we plug in for here, n would represent 52 because it represents the number, or the term in the sequence. Okay, a sub 1 represents your first term, and r represents your common ratio. So remember that common ratio is what you're multiplying by to get from one value to the next. And that's what that common ratio represents. All right, so that's kind of our general formula. We're going to go through some examples here in a bit. The other formula that we're going to talk about right now is our sum of a finite geometric series. So there's going to be a couple of formulas that we're going to use. The finite geometric series. So finite means that it has an end. So in other words, if I asked you to add up, I don't know, like again, the first 26 terms of this geometric sequence, that would be a series, then that would be a finite number of terms in the series, and then you would use this formula. So this one is a little weird, but let's go ahead and go back to this page and let's write this one down. So this is, I'm going to go S of n equals a sub 1, 1 minus r to the n over 1 minus r. All right, so again, this is for a finite geometric series, and so we are going to get into one that's infinite, so if it's helpful to you, you may want to write down finite after it. Again, so this means how many terms you're adding together. So if we're talking about the 13 term, it would represent 13. This is your first term, your common ratio, however many terms we're adding together. And so the formula is a little different. We have to make sure we're following order of operations correctly, but we'll get into that in a couple different examples here in a second. All right, if you don't have some handy, but I would like you to grab some paper because we're going to go through a couple examples that are not in your student journal. All right, so these are some examples, and again, you can pause the video if you need to go grab some paper. These are some examples of just kind of like what you're going to be expected to do with geometric sequences and series. So like arithmetic, what you're going to be asked to do is to write a rule for the nth term. And again, what that means is just writing the rule to represent to get to every term in the sequence. So the first thing you want to do is you want to figure out what your common ratio is. So kind of like figuring out your common difference, right? So the first thing you're going to want to do is figure out your common ratio. So we know all of these are geometric, right? Because, well, that's what the section's about, and that's what I'm telling you. Once we get things mixed up a little bit, you would have to then determine, is this geometric, arithmetic, or maybe even neither? And so that's where it gets a little bit harder, but we'll get to that in a bit. Okay, so geometric. How you figure out the common ratio is you take the, let's say in this case, you take the second term divided by the first term. So 2 divided by 6 is 1/3. And then you would do 2/3 divided by 2. Well, 2/3 divided by 2, like the same thing as saying 2/3 times 1/2, which if you did the math there, gives me 1/3. 2/9 divided by 2/3, I would get, you guessed it, 1/3. So my common ratio here, how to figure it out is take kind of the second term divided by the first term, the third term divided by the second term, the fourth term divided by the third term. So what I figured is my common ratio is 1/3. In order for us to write the rule, we need our common ratio and we need our first term. Just like with arithmetic, we needed a common difference in our first term. With geometric, we need very similar, but we need the common ratio in the first term. So I'm going to go ahead and start with my equation. So that's that one that we just kind of talked about. This is our general form for a geometric sequence. I'm going to plug in what I know. So this one I've already kind of given you basically all the information. There's not any simplify. That would be your equation. For those of you who are familiar with exponential relationships, what makes a rule or an equation an exponential relationship as opposed to, say, quadratic or linear or any of the other ones we've talked about, polynomial, is that the variable is in the power. So it's not like x raised to a power, right? It's a number raised to a variable. So a number raised to n or a number raised to x. That's what makes this one different than any other function you're going to talk about. The variable is the power. And so when you see that, this is the general form for an exponential, or in this case, geometric sequence, when the variable is in the power. So I want you to kind of keep that in the back of your head, because I want you to, we're going to start remembering that, you know, especially when we're starting to identify what kind of functions these are, or what kind of sequences these are. All right, here's another example. So this is very similar to the one I did with arithmetic. I'm giving you a point of sorts, right? So I'm telling you a specific value, a specific term in your sequence, and I'm giving you the common ratio. So unlike the last one, where I gave you the common ratio and the first term, really, I mean, you could figure out the common ratio and then you knew the first term. We don't know what the first term is. So what we're going to do is we're going to start by using our formula. And just like we did with arithmetic, we are going to solve for our first term. So we're going to use this input, output, this point, and plug it into our equation. So a sub n can represent any term in the whole sequence. So we're going to let it represent the fifth term, which means a sub n is equal to 32. Our common ratio is 2/3, and n represents 5. And I know n represents 5 because this is my a sub nth term, which means it's my fifth term, and it equals 32. So here you're going to have to do a little math. Follow your exponent properties. This is 2/3 to the fourth. So 2/3 to the fourth, 2 to the fourth power is 16. 3 to the fourth power is 81. And then in order to solve for a sub n, you're going to divide both sides by 16 over 81, or in other words, multiply by 81 over 16. And so you do that, you get 162. All right, so how that's helpful is now we know our first term. We already knew our common ratio from what we were given in the problem. So now we can write our equation. So we start with our general equation. We plug in what we know. So we're going to plug in 162. We're going to plug in 2/3. And this would be our formula, or our nth term rule. All right, let's do a couple more. All right, similar to what we did in the last one, this is, I'm giving you basically 2 points, and we're asking you to write a rule. This one gets a little more complicated. It's not quite as easy to figure out as what we did with the linear one, with the arithmetic. But nonetheless, we're talking about finding, basically we have to solve for a sub 1, and we have to figure out what our common ratio is. So you can kind of, I guess, common sense your way through some of this stuff. We know the third term is 20. We know the sixth term is negative 160. And so ultimately what we're trying to figure out is the first term and what we're doing to get from one term to the next. So you could figure out, okay, so there's 1, 2, 3 jumps, right? And this is not a linear function, so we can't just divide like our difference by 3 because we're not increasing, but you can kind of think about what are you doing to get from one value to the next. So what I want you to recognize is that, number one, you're going from 20 to negative 160. So your R value needs to be negative. So in order for us to be, in order to get a value of negative 160 down here, we know we're going to have to multiply by a negative value. And so you can kind of play around with this and figure out what value that you're multiplying by to get to negative 160. And then you could use that to kind of work backwards and figure out a sub 1. That is an option. And that does work okay when you're given terms that are kind of lower, like, you know, a sub 3 and a sub 6. If you were given like the 132nd term and the 295th term, probably wouldn't work out so well, okay? So this method, this kind of common sense method will work. Again, I'm looking to kind of like for your plan or what you're doing to figure out your problem. So if you're going to do it this way, if a problem does allow you to do it this way, just make sure you're explaining to me the process. Let me show you the more mathy way of doing this though, because I want to make sure that you can do this for any problem and not just, you know, the ones that are easy to figure out on our own. So what we're going to do is we're going to write this, we're going to set up a system of equations, which I know you're probably like, great. But we've done a lot of work with systems. I know you did a lot of work in Algebra 1 with systems. So this is going to be just kind of a review. So what I'm going to do is I'm going to take this equation here. I am going to start with my general formula. I'm going to plug in this term into this equation. So I'm going to let a sub n represent 20. I don't know what a sub 1 is. I don't even know what r is, but I know n is 3. So I'm going to write down 2 up here because 3 minus 1 is 2. So this is my equation. All right. I'm going to do the exact same thing for this one right here. So I'm going to plug in, I'm just going to use this formula. So I'm going to do negative 160 equals a sub 1 r to the n minus 1, which is 5. All right, so if you notice, I have two equations. So I plugged this point, kind of basically I plugged this point into the equation, I plugged this point into our general equation. We have two equations with two unknowns. That's how we know we're going to solve a system. The easiest way to do this is to solve a system via substitution. So what I'm going to do is I'm going to take one of my equations. I'm going to start with what I think is the easier of the two, which this one, less, I guess, negative 160 is a little scary, r to the 5th maybe. And I'm going to solve it for a sub 1. So in other words, I'm just going to divide both sides by r squared. And once I do that, I'm going to now plug this into my equation for a sub 1. So I'm going to use the substitution property. So I solved this equation for a sub 1, and I'm going to plug it back into this equation where I see a sub 1. So that's what it would look like. So let's simplify this. So this is where those exponent properties come into play. 20 divided by r squared times r to the 5th. I would get 20 times r cubed, because r to the 5th over r squared would give me r cubed. I'm going to divide both sides by 20. And then I'm going to take the cube root. So we do this obviously after we've already talked about our cube root functions and so forth, so that you can solve this. The cube root of both sides, remember that this would be a negative 2. So to get from 20 to negative 160, if this is my third term and my sixth term, I'm going to multiply by negative 2 each time. All right, so that was important. We figured out our r value. Well, now all we have to do is plug in r. Let's go back to here and solve for our a sub 1. So 20 divided by negative 2 squared is 4. So that means a sub 1 is 5. All right, so now we have the two pieces of the puzzle that we need. Let's write our equation. So remember, our equation is in this format. You're plugging in your a sub 1, you're plugging in your r, and this is the rule for the nth term. So again, I showed you this way in case that you come across some problems that aren't quite as easy to figure out common sense way. And so that way you're, have another plan. So you're setting up a system. It's a fairly basic process, but you're setting up a system and then solving for r, plugging it back in, and solving for a sub 1. All right, to end this, number 4, the last one here, what we're going to do is I'm going to ask that you find the sum. So again, notice that I didn't put any words in here. This little summation notation means find the sum. This is the sum of a finite series. So remember we talked about on our formulas, let me go back to this. This was the formula for the sum of a finite series. How we knew this one was finite is because it starts, this is kind of what I plug in k to get my first term, I plug in 6 to get my last term. So there are 6 terms in this series. I plug in 1, I plug in 2, I plug in 3, I plug in 4, I plug in 5, I plug in 6. So there are 6 terms in this series, which means it doesn't go on forever, implying that it's indeed finite. How you can tell it's geometric and not arithmetic is look at your equation. Notice how you have a value, so like in this case 5, raised to a variable. Anytime the variable is in the exponent, that is your indication that this is an exponential, or in this case, geometric relationship. It's not linear, it's not arithmetic. So the variable is the power, which tells you that it's a geometric series. So again, you could do this two ways. You could literally expand out this series. So I could plug in 1 and go 5 to the first power is 5. 5 times a half is 2.5. And I can plug in 2. 2 to the second power is 25. 25 times a half is what? 12.5. And then so forth and so on, right? Up until I plug into 6. And then I could add them all together and get my sum. Okay, that's one option. The other option is to actually use the equation. So I'm going to show you both ways just so that you can see, because sometimes it will be beneficial to maybe do it all by hand if it's really low. If it's only like 6 terms, not that big of a deal. But if you're talking about adding, 392 terms, probably don't want to add them all up like that. Okay, so here's our formula for a finite geometric series. So we are going to add the first 6 terms. So we're going to say S of 6. That's the sum of the first 6 terms. Ace of 1 is your first term. Notice that when I wrote it out here, ace of 1 is 2.5. How I know that is whenever I plug this number into my equation, that gives me my first term. So if I plug in 1, whatever I get out of there is my first term. My common ratio is what you're multiplying by every single time. So you could kind of look at your sequence or your series here and see what your common ratio is. Another way of looking at your R value is your R value is always this number that's raised to the power. So remember in our general equation, go back to our general equation, see how it's R raised to the n minus 1? R is your common ratio. R is what you're raising it's what's being raised to a variable. So R to the k power in this case. So my R is actually 5, and n represents the number of terms, which in this case is 6. Be very careful here with order of operations, okay? So what you have to do, and I'm going to do this in steps so that you can see it. So the first thing I would do is let me find my calculator here. I would go ahead and figure out what 5 to the 6th power is. So 5 raised to the 6 is 15,000. So 1 minus 15,625. So I'm going to simplify this numerator, and I can go ahead and just write down -4 on the bottom. If I did 1 minus that answer, I would get -1,000 or 15,624 divided by -4. Okay, so now let's do that part. Let's do what's inside the parentheses here. So I get 2.5 times, and this becomes 3,906. And then if I multiply by 2.5, I get 9,765. So when you are practicing this, I know it seems somewhat beneath you, but make sure that you are, even though you understand this process, make sure you're able to get the right answer. Because there are a lot of mistakes that I see made just from omitting or putting it into your calculator wrong or not following order of operations, all kinds of stuff like that. So be very careful because I do see that mistake a lot. So when you are trying these answers on big ideas, go for accuracy. If you're not getting the right answer, please let me know so I can see what you're doing on your calculator and I can help. All right, practice this stuff. If you have any questions, come see me. All right, bye for now.